Hello. In this video, we're going to talk about a second-order effect or a non-ideality of the MOSFET transistor. And that one is channel length modulation and its effect on the output current. And so we have second-order effects. Channel length modulation. Now the key here is that we assume that once the transistor enters saturation, we said the drain current or the drain to source current becomes independent of the VDS voltage, and so further increases in VDS will not yield any increases in drain to source current. We represented that graphically. Now, our IV transfer characteristic as follows. There was, for a particular value of overdrive voltage, VGS, or a particular value of VGS, we said once we have entered the saturation region, meaning once VDS reaches the value of VGS minus VT, threshold voltage, or the overdrive voltage, then the current remains constant. Right, like a perfect current source, a perfect transconductance device, where it's only dependent on the input voltage VGS. In reality, and we had talked about, by the way, when we talked about the structure of the transistor, we had said, well, right at this point, at the edge of saturation, the channel becomes pinched off on the drain side, and then it recedes. So my effective channel length is shorter. But yet my electrons keep flowing, my current keeps flowing because the electrons have enough kinetic energy to jump over that gap all the way to the drain. And we said the kinetic energy increases as the field increases, and the channel keeps receding as the field of VDS increases, and both effects counteract each other, meaning the channel recedes more, but yet the kinetic energy is larger, so both effects counteract each other to yield a constant current. In all reality, that's not the case, and the current is going to increase slightly because of those kinetic energies getting higher and higher as VDS increases. And so a more accurate picture, taking into account channel length modulation, will be as follows. Once we enter the saturation region, there is a slight increase in drain current with respect to VDS. I'm going to draw another curve just so that we can see the effect of it more clearly. And one last one. So, and what this basically represents is that there is a non-zero slope to this curve in the saturation region. And of course, this slope is current over voltage, but it represents the inverse of the output resistance. It tells me the current varies with varying loading conditions, and that means my current source, my transconductance device, essentially has a non-zero output, a non-infinite output resistance. The way I model that parameter in my equation, or I introduce this dependency on VDS into my equation, because remember, once I enter saturation, the equation I had for my IDS was that it was equal to 1/2 of Kn VGS minus VT squared over the overdrive voltage squared. There's no dependency on VDS. So I need to introduce another term if I want to model this dependency mathematically. And the way we model it is with a parameter called lambda, which is referred to as the channel length modulation parameter, because what it is essentially modeling is the modulation or change in channel length as I increase my VDS beyond the overdrive voltage. And you will notice that as I keep drawing the extensions of those lines with their slopes, I almost don't have enough space there, but they will intersect that x-axis at a location, so they will all come together at a location on the x-axis, which when we were talking about VGATs, we refer to as the early voltage, and we said that location is equal to negative the early voltage. In the case of MOSFETs, we typically don't talk about early voltage, we talk about the lambda parameter, or the channel length modulation parameter. Now lambda has units of 1 over volt, or volt to the -1, the inverse of volt. And so essentially this will be equal to -1 over lambda. So if you wanted to correlate it to the early voltage, it will be the inverse of the early voltage for the BJT. But you can see that it models a similar type of effect. In the case of the BJT, we had base width modulation. If you recall, in this case it's channel length modulation, but the effect that you're trying to model is the same, is the non-infinite output resistance of the transistor. And so we refer to lambda as the channel length modulation parameter. And it has units of volt squared. And then the other thing to find out is how we enter that into the equation, and it will be as follows. Our ID, taking into account the channel length modulation, will be 1/2 of Kn, the overdrive voltage squared, or VGS minus the threshold voltage squared, 1 plus lambda times VDS. So you can see how now there is a dependency on VDS, which is dependent on lambda. Okay, so this will be my full equation taking that into account. If you recall, in the case of VJT, the term that you introduced was 1 plus, in that case you were talking about collector to emitter voltage, so 1 plus VC divided by the early voltage. This is exactly the same because lambda will be equivalent to 1 over the early voltage. All right. Other effects that are not necessarily second order effects, but that we need to keep into consideration as non-idealities when we are working with MOSFETs, is that first the MOSFETs have a thin oxide layer at the gate, which could be easily destroyed if we apply a continuous voltage of a high enough magnitude. And so we can look into a data sheet what will be the maximum value for that voltage, as well as power dissipation. Just like as we saw with VJT transistors, in the case of MOSFET transistors, they should not be operated beyond their maximum power rating, and there's typically a derating curve or some derating characteristic specified in the data sheet, which tells you this is the maximum power dissipation at, let's say, ambient temperature of 25 degrees. And then if your temperature increases, then you need to derate your power. Basically, as your temperature increases, the amount of power dissipation that you can, the transistor can withstand becomes lower because of that maximum junction temperature. And that's it. Those are all the non-ideal effects that we will cover for MOSFETs.